Okay, so today we are. So in the last class yesterday, we broadly said what gravitational waves are, what are the sources, and so on. Today we are going to diffraction. Okay, this is very interesting, and some can argue that it involves more physics than even the sources because every part of the detector actually involves quite a bit of physics. That's a good part, but the bad part is that we cannot cover it in the class because each component of the detector, even to get a broad idea, like laser, let's say you want to see how much laser power is necessary and things like that, that takes one full lecture, or a little more than that, actually, probably 1 or 2 hours, okay, typically to work out the whole thing. But then that does not mean much because anyway, depending after 1 or 2 hours lecture, you forget it after some time. When I forgot it, right? I did it after PG. But so the thing which we will do is what more or less you will remember. Okay. And that I can do because I remember. So that's how we will go. So let's start with the history. The first detection of gravitational wave happened. I don't forget when the paper was published in 1970, I think. And then they got a Nobel Prize in some year. I forgot all those details. But the thing is that this observation was of a binary pulsar, a Hall-Stellar binary pulsar. It basically, when two neutron stars go around each other, like we discussed yesterday, they will emit gravitational waves. As a result, they will lose some energy, which will make them come a bit closer. Okay. Now, what actually happens is that orbital shrink is very small, but that affects in the perihelion, basically. See, suppose you have just two static objects like the sun and the earth, and you know there are two specific dates when the earth comes the distances are the closest and the farthest. So this ellipse, suppose there was no loss in the system, would be fixed, would be frozen. But if it is not fixed, then this ellipse will slightly start precessing. Okay, and that you can measure, and that will tell you that how much phase has been accumulated in this process, and then that can tell you that how much energy is lost by the system. Okay, so that's what was done, and this is that cumulative shift of periastron. Now helion is for sun, but periastron for this time for the binary pulsar. This measurement was done, you can read, 1975 to 2005, 30 years. You would not believe, like 30 years observing the same thing. So people did. And you see the result is so nice that these dots here, there are error words actually. This thing, these are the measurements, and this solid line is the prediction from general relativity. And they match very well, okay? Some of these observations were done in recent times. Initial observation was, I think, up to this point. So this was done by Hulse and Taylor, and they got the Nobel Prize for this part. So this was an indirect detection of gravitational waves. Now, what is the indirect detection part? Now, suppose it is like this thing. So suppose you have a cup of hot tea or something, okay? You know that the distribution, suppose it's a black body. Let's say you have a black body. And you know that the black body, you have come up with a theory that the black body radiation is Planckian. Okay? But you don't have a device to measure the exact Planck distribution. But then you say that, well, if we integrate this Planck distribution over all the frequencies and so on, then we get Stefan-Boltzmann cooling law. And you only have a thermometer. So you put the thermometer in that coffee or whatever, and then you see how the temperature is falling. Okay? And then you say that, see, if my theory is right, it should lose temperature in this way, and that is what is happening. So this is like this, that if this system is losing energy in a certain way, as predicted by general relativity, then the orbit is going to shrink in a certain way, and that exactly matches the prediction. Then you say, okay, then there's an indirect detection, and hence the conclusion is that government should put more money for that for direct detection. Okay, so now we come to the direct detection part. How do you actually detect gravitational waves? So now we have to get into a little bit of mathematics. First, I will tell you graphically what is happening, and then we'll have to see like what exactly it is. So when gravitational waves fall on a ring of particles like this, the plus polarization, then it distorts this thing in this way. So it is like it works. It starts doing, just consider the ring right now, it's this kind of distorting business, okay? And the cross polarization, as I said, it will do exactly the same thing at 45 degrees, and that's what it is doing, okay? Now, why is it happening like this? For that, we have to do this complicated mathematics, but it's not complicated, so let's do it right away. That will be a good application of what you have learned in your general relativity course. So now let me ask you. So let's say that this is ds square is the event separation. Let's say we want to consider light propagating along a certain direction, and why certainly where from where light comes. Okay, so we generally measure distances in terms of light travel time. So let's say that there are two events somewhere. Let's say we can take these 2 points. Okay, let's say along the x-axis there are 2 events. That is, events means what? We are considering so some space coordinate and time coordinates. Okay, gravitational waves are falling along the z-axis. So we don't consider z. We are only considering x, y, and t. Okay, 3 coordinates. So an event would mean along the, if we go along the x-axis, the x coordinate and time coordinate. Okay, so the separation is given by this ds square that you know. Now, okay, so let's say that when we say that this guy gets distorted like this, what is meant by that? What exactly changes? What we are basically saying is that if you take the light travel time between, let's say there is a center, some fiducial center like this. Let's consider here then, the fiducial center here. That this light travel time along this path and along this path are compared here, basically. That's what it means, right? Because what are you going to plot? Okay, one important thing I did not tell you, right? This will make things even more confusing. This is why I should tell you. Is that in a TT gauge, the coordinates of the particles of suppose you had some test masses, when gravitational waves fall, do not change. So when you are in TT gauge, the coordinates are not changing. Suppose something had a coordinate x, y, it is always going to stay x, y. Okay? So then the problem is that then what exactly is happening here? So what is changing is the metric, but not the coordinates, because these particles are freely falling particles, sort of. Like they are fixed in some sense in that coordinate system, they are frozen. Okay? At least in one direction they are freely falling. Let's say that you are hanging something, which will come later on, then it cannot move along the vertical direction, but it is essentially freely falling in the horizontal direction, in x direction or y direction. Anyway, let's now come to it. So what we have to do to find this shape is that you find the distance light travel time from the center to this point and to this point. Then you will see that if that is changing, then you know that it is getting distorted. If it is constant, if x and y are the same, then you know it is remaining retaining its shape. If it is the same and not changing, then there is no effect of gravitational waves on this ring of particles, right? Not clear. Okay. So what I'm saying is that let's consider this point, which is supposed to be a test point, but that will come later. And this point, okay. When gravitational waves are falling, in that, let's say we are considering TT gauge. Why TT gauge? Because then that matrix, the effect of gravitational waves on this tensor we wrote 4 by 4, has only 4 components and it becomes very easy. In fact, for one polarization, there will be two components and only one independent component. So that's fine. Let me remind you, because I see blank faces. Basically, we're talking about this one. Okay. When gravitational waves come, if you use sticky gauge, then only these four components are non-zero, everything else is zero. And of course, you agree that more zeros make life much simpler, because then you don't have to consider a lot of components. And when it is plus polarization, only these two components will be there, and these two will not be there. Right? So it's a diagonal vector. And that too, only one component is independent, because this is H plus and this is minus H plus. Okay, so we'll then have to worry about only one component. So this makes life very easy. But in that coordinate, the actual coordinate system, the coordinates of individual test masses are not going to change when gravitational waves come, because it is only the metric fluctuations. There is no force there to move them. See, in general relativity, gravitation is vision as a change in space-time geometry. There is no other force. You can add a force, like you can add electromagnetic force, etc. But right now there is no electromagnetic force or any other force. So they are just going to stay like that. The coordinates of the particles are not going to change. At this stage, how do you determine, suppose there was this ring of particles, and you want to determine that when gravitational waves fall, what is going to be its shape? Okay, so what do you do? The coordinates are fixed, everything is fixed. The only thing that can change is the light travel time between this. Okay, so let's calculate the light travel time. Now I think you more or less understand. Okay, so how do we get the light travel time? So you have to start from somewhere which we know very well that okay, this is the good starting point. The good starting point is also for light travel, because when light goes from one point to another point, okay. So I think you have seen these space-time diagrams, right? In your that light is given by this 45-degree light. This is fixed. It is not only true in special relativity, but this is also true in general relativity. And that is the starting point of general relativity. Okay? See, when in special relativity, what happens to this is that you do this. Let's say we are taking one dimension, but one and multiple dimension doesn't matter. In special relativity, this condition holds in every coordinate system, right? This is for light. This is the basis of special relativity. And this meaning this in any other frame also this will remain the same. Okay? In general relativity, what happens to this? Do you know what happens to this? This says zero because this is a scalar. Okay? You know that this is a scalar because you could also write it as a scalar product between two four vectors. Like you could write this as this. I don't know whether you know all these indices, but this is essentially a scalar. It is going to remain the same. General relativity tells you that at every point you can have a locally inertial frame. Okay? This sounds very profound, but all it means is that for every surface which is smooth and continuous, you can have a tangent. It is exactly that what it meant by that. Okay? So that means if you go to that tangent plane, which corresponds to a freely falling frame, okay, that's like a flat, that is a locally flat inertial coordinate system, then this d square will transform to something, okay? But there, since it is locally inertial, you know that d square has to be 0. And change of coordinates do not change a scalar, so d square is going to be 0 everywhere. In fact, the general relativity is formed in the other way around. It assumes that d square for light is going to be 0, and then you back calculate and get into a Gauss geometry and so on. Because equivalence principle, which is that Galileo's experiment, is the starting point for general relativity. Okay, it assumes that equivalence principle holds and so on. There are of course different versions of equivalence principle, strong equivalence principles, etc. But we are not getting into that. I think you have 3 lectures, right? These things were covered, right? Local inertial frame, these things. Okay, fine. So I am just repeating so that, like, you know, okay, fine. Now let's come to this. So this, whatever it is, this is correct. This dl square is equal to 0 for light. That's there. Okay? So now let's see. So let's say light is going from this center, which is 0, 0 to this point. Okay, first let us take the one-way diagram. This is x, 0, L, 0. Let's say this is called it capital L. That is the length in that direction. Okay? So what we are going to do is that, so, and we are going to measure what? That light travel time. So all we have to do is to integrate this dt square. It is as simple as that. But wait a second, this is in Minkowski. So you have to first write it in this coordinate system, which is not Minkowski. Then things will get a bit complicated. So what we have to do now is we have to write this in terms of minus. Well, this is first we'll keep it as plus, because here it came as minus because the g excess, these things were minus. Okay? Why I did not write any other terms? That is, there could be dt dx, dx dx, all those things. That is because the metric we chose was g mu mu equal to eta mu mu plus h mu mu. This is the metric we are working with. Okay. For plus polarization, okay. Let's see what is the plus. So let me write down this metric. So then it will become even clearer. This I like this here and this here. This metric is 1, minus 1, minus 1, minus 1, and all components 0. Okay, this is Minkowski metric. See, this when you use this metric and put these 4 vectors, which are c dt, dx, dy, dz, and contract it, then suppose we put that one thing here and one thing here, then what happens is that you get this dx, c square dt square minus dx square minus dy square minus dz square. That's how it comes. This is the Minkowski metric. Now let's see this h mu mu part. What we will get here is that again it will have the diagonal terms. This two will be 0. This term is h plus. This term is minus h plus. And again 0 and 0. Okay. Then if we took the cross polarization though, then this term would not be the same, because then you would have an xy and yx component. Even though you could always 45 degree rotate things and do it, but anyway, so there will be those components. Now if I put this component back there, what is going to happen is that, what is G00? Now you tell me, what is G00?
1.
It is 1, correct. I will actually put a c squared here, because otherwise the units would not match and you can. Okay. So it is, I put c squared, it is, so you could take the x0 component as time. Many people take time because people use c equal to 1 units, but it is better to put it, so I put c squared dt squared. So then G00 is 1. Okay. Because this is 1 and this is 0, the sum is 1. Fine. So we get first term is c squared dt squared plus, and now the second term. Okay, I'll put plus and then come back to this. What is gxx? Now why did I say xx? Because you know this plus, cross, etc. gets a bit confusing. Which direction is plus, etc. So xx means this component. That is x comma x. What is going to be?
Minus 1 plus x.
Then
Plus h.
Plus h plus. Correct. That is the thing. Plus h plus. Yeah. Dx squared. That's all we need. Okay. Now I will run this part. Now, for light, since this is 0, all we have to do is to equate this and integrate. That's about it. So now let's see, then what happens is that you get here c square dt square equal to, I'm taking this to the other side, so it will become 1 minus h plus dx square Okay, that means the total time taken, which let us call it, say, say delta t, is equal to. So I am integrating this part basically. I am for time. So we put a 1 by c here. Integrate from 0 to L. 1 minus h plus square root. So let's say half dx, right? Okay. Now, what I am going to do is to take this term out. Okay. And I say 1 minus h plus by 2 into L. Anyone has any objections to this? No. Almost. But there are many questions that how did it happen? What could go wrong with this?
X plus is really large.
That's right. Then you cannot do it. This assumes that h plus is very small, right? So, which is a valid assumption because it is very difficult to get a large signal on the Earth. Other thing you could argue is that if what happens if x is so here I have written all this, but then h plus could be dependent on x and t. Okay, because I am just saying that this is a constant. We'll come back to that. Let us assume momentarily that it's a constant.
But we are far away from.
Even then, so you can see that we are far away from the source,
Right.
and you are sliding on a wave. What is a good assumption is that if we are far away from the source, then the x, suppose the source is here and you are looking at the floor, then most likely the waveform is going to be pretty homogeneous. So you don't have to worry about the change in h plus in the horizontal direction. Okay, like along this thing, even though the source could be on that direction, but let's say that is this you don't have to worry about. But then we are saying that we are measuring a wave which has a certain frequency. It has to be a function of time, right? We'll come back to this. So for the time being, assume that the time taken, time scale over which this thing changes, h plus changes. H plus is indeed a function of time. That's what we measure. But the light travel time is much smaller than that time scale. That is, the period of the gravitational waves we are or the source which we are trying to measure, trying to observe, has to be much larger than the light travel time in the between these objects. Okay, otherwise there will be a difference. Okay, so I am actually mixing the discussion and the measurement part, but you can see that that is where we are getting. That we want to study the effect of gravitational waves on a set of particles so that we can measure, detect it. We'll come to this complicated part later on, that how we exactly do it. But for the time being, assume that this is small. In that limit, this delta t, that is one wave length, let us call it delta t1. That is light going from here to there. That the center, the beam splitter to 1 meter will be given by this. Okay? Now it has to come back also. So now it is okay. Before that, now suppose there was no gravitational wave. Then what would be the change? What would be the time required to go? It will be obviously simple L by C, right? So then, what is the phase change or the time difference that was introduced by the presence of gravitational waves? So if we call it small delta T1, that will be delta T1 with gravitational waves minus delta T1, let's say 0. Right? This will be the change which was introduced because by gravitational waves. This is going to be Yeah. So you can say minus H plus L by 2. Okay? Sorry, C. Yeah. C has to be there. Okay? Now, you see that when I will just checking one important thing. Yeah, we should find. So the thing is that when it is going from one direction to another direction, we had some equation when the light was propagating from the origin to L. When it comes back, okay, actually the same equation applies because there are all squares, delta dt square and dx square. So you get exactly the same change when light returns as well, right? There is no difference that way. So the total change, this is one way. So the total change along the x direction for a round trip is going and coming back becomes minus h plus L by 2c. Now we see that h plus is actually sinusoidal quantity. That minus plus does not matter. Okay, basically all what we are going to look at is the amplitude of this. So you can just remove the minus and write, let's say, the strain signal of the amplitude, let's say h. Then this will be like h L by c. Okay, nice, fine. So this is along the x direction. Now the next thing we have to do is to get the, not this is not x, this is ct. Yeah. Next thing is we have to get the same thing for this on this side. Okay. Now if you look at this equation here, I hope online people can see all this. What else can be done? Now if you look at this equation, okay, when you take light propagating along the y direction, what will happen here? Just dy square. So the whole calculation is going to go through. Basically, this will become gyy. Now, but one important change happens here. Can you spot what happens here in this line?
Sign.
This gets a minus sign. That means that if you have this delta tx as something, delta ty will have a minus of delta tx. Okay? That means, now let us come back to this thing. So what is happening is that when one R or one direction is increasing, the other one is decreasing. Okay. That then, this is the important, oh by the way, I had all these formulas written here. I hope these are all consistent. Yeah, hopefully. So, so the last thing I will just write what was written here. So you see that the total, so if you know the light travel time difference, which is delta tx, you could also convert it in terms of effective length change, right? So that means this delta tx into c, if I do, that will give you some kind of effective change in the light travel distance instead of light travel time. And if you divide it by L, or you can call this quantity, let's say this part, you can call it as delta L. This is, I'm writing this because this is the usual way of writing a strain signal in elasticity, for example. So then what you get is this delta L by L, and that this C delta X by L. You see that this is this. So if you multiply by C, C cancels out, and this L will be divided. So this becomes H. Okay. Here, what is there is also Ty minus Tx. That's a different thing. That I will come to that later on. So for one particular direction, this is the strain. So gravitational signal produces of strain H, that same H which appears in that metric is equal to the strain in the seen in a body, like delta L by L. It's not completely true because it is the strain is H by 2 really, because it is one way was H by 2, but if you take 2y then it becomes H. So it is of that order. Okay, fine. Now, wait. Now let's come back to the detection problem. Okay, we'll come back to all these other things later on. This so just because this image is there and you can see that if you take one rod along this line or two test masses, then what we will see is some fluctuations which will be sensitive to XX component. And this one will be sensitive to YY component and so on. So even with one, you can do something, some detection. But if you have an instrument which can measure the difference in the path lengths, then what happens is that because they have opposite signs, the path length actually differences doubles. Okay, that is delta Tx minus delta Ty. That thing actually doubles here. Okay? Meaning, if you take delta Ty minus delta Tx, would be twice minus delta Tx. That's all. So then this gives the idea that maybe we can use an interferometer, which is very sensitive in getting the path length and many other reasons also. That an interferometer also does something, which is why it is so important. Let me check the chat now. How do I get this chat? This is very interesting. Okay, I don't have the chat question, but there is a chat thing coming there. Okay. See here, it shows them the question, but I don't see it. Okay. Now let's move on. So I guess this is the only mathematics that is involved. Right? I guess you have it is clear, right? That
recording stopped.
Cross
Recording in progress.
Which one?
the X cross, we said there will be the X.
That is right. We did not do that part, but you can do it at home. Okay? That if you try the cross polarization, then this will change. You have to also consider the dt dx term. This will be slightly more complicated, but not too complicated. You will be able to do it. Okay. So there will be a dt x term that will have the cross component, that H plus component, and then you can basically do this calculation. I forgot exactly how much you will be able to do it. It's not a big problem. Okay. Yes.
When did you use that the coordinate would change as the gravitational wave passes? You had mentioned that
coordinates don't change when gravitational wave passes because there is no other force.
No, as in when you didn't use that in the.
I did, because when I integrated that, see, I put this upper limit as L. If coordinate change, this would not be L. Okay, that is where, yeah, good point. This is where I used it.
But the change would be small only, right? So
no, but everything is small. This whole change is small. Here, when we are saying that this H plus is nearly constant, that is a different question. But essentially, the change is going to be small. Yes. Metric. Meaning the small g unit, small one is the metric. The capital one is Einstein's tensor. Meaning this one is the metric. And this H mu nu is called metric perturbations. Usually people use G mu nu and H mu nu. And then figure out in the context that we are talking about the big G mu nu or the small G mu nu. Okay? Okay. So now let's go to the first attempt for detection. So this was done by Weber. He made this bar. It's called a resonant bar. Okay, detector. So what happens when gravitational waves fall on this detector is that because it is elastic, it is going to prevent any deformation in its length. But nevertheless, the elastic forces are there. So there will be standing waves created when gravitational waves are passing through. And if the resonance frequency of the bar is matching the gravitational wave frequency, then this will basically start ringing. Okay, start oscillating. If you could measure these vibrations through very sensitive sensors, such that the sensors themselves don't perturb the system, because when you are sensing something, you have done these experiments, like thought experiments. I think in quantum mechanics for uncertainty and so on, that how do you measure the position and so on. It is like, I think some ghost or something it used to be called, that somebody is sending a photon, the photon will hit, that will create uncertainty. This is for Heisenberg's uncertainty. That means if you try to measure the position by sending photons, you will actually end up not measuring it. The same things apply here in gravitation. That the most interesting thing is that gravitational detectors are actually very sensitive quantum detectors. You basically the aim is to reach that quantum uncertainty level, okay? And people not only reach that level, they go beyond it. And you may think, like, how can you beat the uncertainty principle? You can actually tweak the uncertainty principle in such a way, it's something called quantum squeezing, where you squeeze the uncertainty circle to an ellipse so that you can measure phase better than amplitude. So you compromise with amplitude measurement and measure phase better. But anyway, those are there. But so this is the main idea here, is that when you are trying to measure those perturbations in the bar, the sensor should not perturb the bar. So that is the primary challenge. Okay. Now this one, the problem here, there are multiple problems with this kind of detector. First of all, this is one direction. It is sensitive to only one direction. It's an omnidirectional. That is, if you have X and Y, then you could detect from other directions. Then there's a resonant part. In order to have very high sensitivity, that is to measure small signals, this bar should have very good quality factor. That is, any small perturbation should really shake the bar, like, as much as possible. But you also know that when, if you remember your class 12 days, those resonance calculations, that forced harmonic oscillation problem, that when the quality factor is high, it implies a very low bandwidth, because it is only sensitive to a very small narrow frequency range, which means that if a signal, gravitational signal, is scanning through the frequencies, which is what happens for binaries, because continuously the period is changing. So only for a very short time it will be able to observe that. So which means that what is called the signal to noise ratio, that is, the sensitivity of the detector is going to go down quite significantly, because the whole idea of telescopes is to integrate for a longer time. If you cannot integrate for a long time, your instrument is insensitive, right? That is why we cannot see very distant stars with our own eyes, because eye has 1/10 of a second's integration time. But even if you have a mobile phone, you can often catch the galaxy, which you cannot see with your normal eyes in certain conditions. If you use like 30 seconds integration with your phone, you may be able to, in some phones there are this astro mode, you may be able to see the galaxy. So this is the main thing. So that increases the sensitivity quite a bit. So this you cannot do here. So in gravitational detection, by the way, if I forget, you can remind me how this integration is done. It is very much like what we have in electromagnetic astronomy, but it's very complicated because of situation, because the frequency is changing. But that will come in the next lecture. So then what people did was that this did not succeed, and also the Brownian motion in normal room temperature creates much more vibration than gravitational waves. So this has to be cryogenically cooled. So that is what people tried later on. There are cryogenic detectors, then there are detectors which are omnidirectional, that they can get signals from different directions, etc. But nothing of these so far have reached enough sensitivity that they can detect the gravitational signal, but these detectors are relatively cheap to make, so which is why people still make them, because if you have a supernova in our galaxy, there may be a possibility that a signal can be detected with these detectors. But the problem, I mean, of course, there could be supernova in our galaxy, but we don't know exactly how much is the gravitational waves from supernova, etc. All the uncertainties are there, but there are possibilities. Now let's come to the actual how it is detected. So this is a Michelson interferometer. It's a very advanced Michelson interferometer. We'll come there, but let's start with that. So light is split from this Bell splitter. It's coherent laser light. So that is why the phase is there, and it comes here. Phase is retained. Then they combine here. It comes to this let's say detector. If the phase is exactly reversed, then you will get zero when there is no gravitational signal. When gravitational signal comes, there is a change in phase, and then you will see the fluctuation here. That's how you can detect gravitational waves. Okay, this is the basic principle. But what happens is that this is not how gravitational waves are detected. That is, this is a very simplistic view of this. There is no phase change happens here. So now we will get into the details that what exactly happens in a real detector. Okay, this will be a bit complicated. So let me first cover the broad things, and then we will come to the actual part, that how it is done. Now they are so even though I said that this is not how it is detected, the basic principle is actually this. There is no other principle. So all the mathematics, etc., what you can do is you can do with basically this understanding. But what is done in reality is fairly complicated, and that is why it is a major engineering problem. Now this is where the detectors presently are. So this is in the United States. There are two detectors at Hanford and Livingston. They are 4 kilometers each. They are separated by 3,000 kilometers, intentionally chosen so that the chances that they detect common noise is extremely low. Okay. Like when a truck passes by or something, there is a lot of noise in this detector. But then a truck cannot create a noise 3,000 kilometers away. So that's how all these possibilities of coincident noise triggers are reduced. There is a detector in Germany called GEO, which is a 600-meter detector, and its sensitivity is very low, but it's one of the most important detectors because most of the technologies, the advanced technologies which are used in LIGO detectors, are actually developed here. Okay. Then there is a Virgo detector, which is a 3-kilometer detector near Pisa, Italy, where Galileo had this did his experiment. This detector has reasonably good sensitivity, but not as good as the LIGO detector, as far as still now, even though they use much more sophisticated seismic isolations. Come to that later on. The detector in Kagra is operating. It is a 3-kilometer detector. It is underground and it has cryogenic detector, but the sensitivity is pretty poor at this stage. And then there is a hope for the LIGO India detector, which is planned for 2030 operating time. The plan is that LIGO India will have the same sensitivity as the LIGO Hanford and Livingston detectors at that time when it starts operating. So then, which would make this one of the most sensitive detectors when it starts operating. So these three will have very similar sensitivity. But then this is completely uncertain because many of you have to work for the detector, and I don't know how hard you are going to work. Because a detector is built by the PhD students. Okay. So now, so this is the LIGO detector. Okay, so this arm is 4 kilometers. Now, why is this arm is 4 kilometers? Why is it so long? Now, if you look at this formula, so this H is what you are trying to measure or trying to detect. That's the physical signal. It's extremely small. It will give that it's like 10 to the minus 22 and so on. This L, now delta L is what you can measure with an interferometer. right? The arm length change, that is what you are measuring. This, because this will change the fringes in the interferometer. So if you make L larger, you have more delta L. Correct? That's the principle. So you want to make this as large as possible. But how large is the question? We'll come there. Okay, let me tell you right away. Now, we have. So the thing is that, so now let us come to all these complicated issues. Okay, now that more or less you have understood what broadly happened, now let us come back to this problem of H plus is a function of time. So what you are trying to do is that you want to measure the fluctuations which is perturbating. That is, let's say this arm is going, so it's oscillating, right? Now suppose you integrate for several oscillations or one full oscillation. What are you going to get? The total integrated phase change? It will be 0 because you have covered one full cycle of a sinusoid. That means if you are trying to measure a sinusoid, you cannot integrate for its whole cycle. Then you will get 0. So you have to, if you want to integrate, you can only integrate, let's say roughly, for 1/2 of it. Okay. Okay. Now, if there is light is going and coming back, let's say two-way process, then that total integration time, and I told you already, right, that when you integrate, basically going or coming back, there is no difference. I mean, it is basically the phase change adds up. So this total time when light goes and comes back should be much less than the, or at most, not much less, but at most, the half the period of the signal. That is one half cycle. Because then you can roughly say that for one cycle, it will completely add up. With the other cycle, you are not adding up, then it will give you the negative signal. So one positive, one negative, one positive, one negative. It does not work exactly that way because it's like in between things and so on, but more or less you will get something fluctuating with much higher sensitivity. Okay? So now, then the point is that if you want to optimize the length of the signal, length of the detector, what would be the optimal length for a detector? Think about it. They're actually similar to radio astronomy and so on. So if you want to have maximum sensitivity of the detector, what should be the arm length of an interferometric detector? Can someone guess?
So that the travel time is approximately similar to the half the period of the solar.
Right. So then, what should be the length?
Not yesterday they said that it will be much more than 4.
That is much more than 4 kilometers. But what is the length? Exact length. You can come up with that, right? Suppose the signal is 100 hertz. Okay, it's very easy. So you are almost there. See, so the signal, it's let's say 100 hertz. What is the wavelength of the signal at 100 hertz? 3000 kilometers. Okay. Now you are saying that the length of the return travel path is half the period. How much is the half period? Means lambda by 2, right? Corresponds to the length of lambda by 2. But that is 2L is lambda by 2. So if the actual length should be lambda by 4. That should be the optimal distance, optimal length for the or 1 hour. Okay. Now 3000 kilometers is lambda, then your detector should be 750. So since the frequency also is not exactly 100 meters and so on, and 100 hertz and so on, it's in that length, so it's basically of the order of 1000 kilometers. That's what you need for the arm length. 1000 kilometers is pretty long, as you can imagine. Even 100 kilometers, even 4 kilometers is very long. You see, if you do a aerial distance from here to Pune station, it will be of that order. And you don't usually walk from here to Pune station. You have to take some public transport. Okay, so if you go from here to the Pune University main gate and come back, this is about 5 kilometers. Okay, So this is how big the detector has to be. I mean, so what said this 4 kilometer? Because it becomes very difficult to get longer arm length on the earth, because simply because you have to buy the land, and it becomes very expensive otherwise. So then what do you do? So you need a 1,000 kilometer detector, but you have only 4 kilometer, 1,000 or let's say a few hundred times more longer detector. What you do, the one possibility is that you can fold the arm length. That is, you put mirrors there and then do this kind of, okay. Like if you did it like for, like say 100 times, the detector will become 400 kilometers long. But that's not a good design. People consider this, but this is not the most effective design. Most effective design, which is used, is this one. It's called a Fabry-Pérot cavity. So what happens is that I think many of you have studied in your course that you basically trap the light. You put 2 mirrors, light goes in, each one is very highly reflective, then it cannot come out. It's as simple as that. Okay, only a small fraction comes out. So let's say this is 99% reflective, and then if you put light, then only 1% of it can come out. So inside the cavity, you have 100 times more intensity than outside, because they are just trapped there. That effectively increases the arm length of the detector by, I mean, if it was 100, it would be factor of 100, but in LIGO what is used is about 300, so it increases the arm length by about a factor of 300. Okay. So this actually, it is not exactly 300. The exact formula is something like 2 into finesse by pi, where finesse is what determines that how many sort of finesse is related to how many times the light is going to go through and so on. But effectively, you come to this sort of range. Okay, now this is one part of it. Okay. So here I will. So one of the main advantages of using the Fabry-Pérot is that you can use a much smaller mirror. Otherwise, if optics becomes very large, and then it becomes very complicated. Here you can use a small mirror. You still use a large mirror. Meaning these mirrors are small, not like this one. This is like 1 foot mirror. But with that kind of size, you can manage. Otherwise, it becomes too difficult to design the interferometer. Everything will go up then. Because the vacuum tubes, which are very expensive, will have to have larger radius. Okay, now this is a slightly more complicated version of the detector. So what happens here is that I'll come to this part later on. As I said, in the Fabry-Pérot cavity, there is much more power inside now. Okay, because of these mirrors. Okay. Now that effectively took care of the arm length, that whatever is the optimal length you needed for detection. So what is going to happen to the signals whose period is more than that is low frequency signal? You will not be able to detect them optimally, because if the period is too long, then that integration effect will actually dilute the signal. So it has to be, so that sets kind of like a lower limit, but the lower limit is set by something else also. We will come there. And now, so basically the power here is somewhat, it increases, not this. It increases by some factor. Then what you have to do is to see that there is something called the photon shock noise, okay, which determines the sensitivity at this range. So see, what I'm saying is that the power in the cavity increases many folds because of this bouncing on and off. Okay, but this power is relative. Like whatever laser power you are putting here, it will be proportional to that. It's laser power times the number of times they bounce. But what should be the laser power? That's the question. Suppose you put here, you see that 750 kilowatt. But if you put 1,000 of the power, it will be 750 watt. But 750 kilowatt is coming because the initial laser power is 125 watt. That was the design. So what fixes that? So that requires some more understanding that you are trying to measure phase. Okay, you are trying to measure phase by looking at interference fringes. Brighter the fringe, if the fringe contrast is larger, you have a larger chart. You would be more sensitive to small fringe changes. Like the fringe was very dim, then you would not be able to sensitive to strong changes. So you have a photodetector there, which is trying to measure this fringe change. Okay, the sensitivity of a photodetector, the photodetector is like a mobile phone camera. At night, you need to integrate longer because the number of photons have gone down, and because you need to integrate longer, the shutter speed increases or speed decreases. The integration time increases, which is why your images get blurred because you are integrating for a longer time. It's exactly the same thing that if you want to, but you cannot integrate here for a long time, so that is fixed. So you need to increase the number of photons in order to detect the signal. When you put all the calculations, so increasing the number of photons means you have to increase the laser power in the cavity. Now, if you do all the calculations, that requires some calculations to be. Actually, these calculations involve on pure like basic physics, and you won't be able to do the calculation because all you have to assume is Poisson noise and put the calculation, all the numbers, etc. That h nu is the power or is the energy of the photon, and all those things. When you put, you get this number. It does not require any extra physics, but it is involved. Like you have to do step by step. There is a book by Peter Solution which has all these calculations there. You can do it. So then you see that it has to be few hundred kilowatt power has to be there in order to reduce the short noise. Okay, short noise will be actually here. It will come here. Like the fringe pattern will be proportional to the power here, and finally it will come there. But then 750 kilowatt is quite a bit of power, and it will require increasing the reflectivity of this, so that if you bounce more times, then the power can increase. But I already told you that you cannot bounce too many times because then you will lose the low frequency signal. That is another problem. Okay, the signals more you bounce, more you are integrating, and you are losing some part of the signal. So that also is you cannot do. Then what exactly is your option? Yeah. So the option then are like this. So you have to increase the laser power, but you can do one more thing. There is something called the power recycling mirror. Okay, that is put here. So whatever light was coming back, put the power recycling mirror and make another cavity, another resonant cavity. That increases the laser power by about a factor of 50. Okay, so this is how then the total amplification factor here turns out to be about few thousand times. So if you take this 125 watt, you see that it has become 3000 times amplified. So 125 becoming 750. So this is how laser power is increased. There are more parts here, but we will not get into that. Okay, now let us move on. So you have basically understood that you need a certain length for the signal, and laser. This is called the storage time. The storage time in this cavity, that is the number of time it is staying in the cavity, should not be increased, because more you increase it, you are actually losing parts of the signal because it will get diluted and things like that. So that is limited. So you cannot increase number of fold, but you have to increase the laser power. Even with this kind of power recycling technique, you have to have very powerful laser. Now 125 watt may not look like a very powerful laser, but it's a very powerful continuous wave laser with very good quality. Okay, when you think here about like very high power, like I don't know how kilowatt and things like that, those are short pulse lasers which are used for cutting and stuff like that. They are not coherent lasers which are maintaining coherence for a very long time. Okay. Now let's go to some of the parameters. I'll come to one more thing I missed. I'll come back there. You see the arm cavity length is almost like 4 kilometer, and then finesse, this is 450 actually is the finesse, but then if you do that 2 into this by pi, then you will get that 300 bounces. Then what is interesting, this 1 feet is the sort of the diameter of the mirror, and the mirror is 40 kilo. Now you are thinking like 40 kilo is like half human weight. Why would you do that? Now let us come back here. The thing is that when you are increasing the laser power in this cavity, okay. In fact, some humans will be almost 40 kilo. It's like almost 1 human power. It's also there. When you are increasing the number of folds in the cavity, you are also increasing the number of photons bouncing on the mirror. Okay? And you might think like, oh, that's like extremely tiny. A photon bouncing on a mirror has absolutely negligible effect, right? The radiation pressure that the photon is going to impart is extremely small. But it is not as small when the laser power is almost a megawatt. And when you are trying to measure the effective distance of effective strain of 10 to the power minus 22, 10 to the power minus 22 means the displacement of the mirror is like, so even if you have a 4 kilometer detector, is about 10 to the minus 18, which is smaller than the size of a photon. This is that small. So at that stage, the radiation pressure noise increases with the number of folds. So that also limits how much you can increase the number of bounces. So, but then, how would you, even with that, how would you reduce the effect of this number of, that radiation pressure noise? That can be done by increasing the mass of the mirror. See, the gravitational effects are independent of the masses, right? So the mirrors, no matter how heavy they are, the effect of the gravitational waves will be the same. But this radiation pressure noise, which is basically radiation pressure noise means radiation pressure is causing the mirror to move. That motion will go down if the mirrors are heavy, because the pressure is the same. If you have very heavy mass, then it will be difficult for the photons to move it. So which is why they use these 40 kg masses. Okay. I mean, initially it was 10 kilo, then it was 40 kilo, but it becomes very difficult to build a good quality mirror of that mass because it has to have the right quality factor and so on. So these are other kind of noise. Come there later. Okay. So now, so this is the sensitivity curve for the detector. The sensitivity curve means that at every frequency, the detector will have some noise. So you can only detect a signal when the signal is above that noise level. At the lower frequencies, at the lowest frequencies, it is dominated by seismic noise. You see this line. Okay, this is ultimately the factor, dominating factor. At the highest frequencies here, it is dominated by the photon shot noise. It's probably written somewhere there. No, it is not written there, but basically what it says is quantum noise. So the quantum noise is the sum of photon shot noise at higher frequencies plus the radiation pressure noise at the lower frequency. Okay, this is the quantum noise. This red line, which is almost tangent to this, actually it is basically the you are trying to limit. Anyway, so this is the coating Brownian noise. So that is basically the mirror as a coating, which is basically does the reflection. The coating is very important, and that is a very active area of research. That how you choose the coat so that the vibrations of the molecules of those coating, the coating material at normal room temperature should not create enough noise that you cannot detect gravitational. You may say, if you calculate actually this noise, you will see that this vibrations of the molecules is actually much larger than gravitational signal. Then you will feel like, how are you then detecting this? The thing is that it is averaged over the whole mirror surface, because that is how we choose a bigger surface, then it gets kind of smoothed out, and then you integrate for many circles. So that's how this gets reduced. Okay, what else? Suspension thermal noise. Suspension thermal. This is somewhere coming here. This is basically the noise. So when the mirrors are, I will show you the picture, are hung by some string of glass. So 40 kilo mirror is actually hung by a glass string. Because if you match the material, then the quality factor is high. So what is this quality factor I'm talking about? Many times I'm saying this. The thing is that there is noise all around. Okay? There will be noise at every frequency range. You cannot get rid of this noise. What you can do, and this is related to your fundamental principle, that at temperature T, every degrees of freedom has an energy. What is that? Every degrees of freedom will have an energy equal to half kT. So if in 3 degrees of freedom it's 3 by 2 kT. That half kT noise you cannot get rid of. But you can do one clever thing. You can have a high quality factor material that is a very highly resonant material whose resonance peak is completely outside the detection band. Suppose you are interested in a kilohertz, in few hertz to few kilohertz range detection. Now you choose a material whose resonance happens at megahertz. Then what happens is that all this noise will then go to that frequency band. And effectively, the frequency at which you are observing will have lesser noise. So these are the techniques which are used. I mean, you can imagine that it took 100 years to detect gravitational waves because it is not going to be easy because you are trying to measure so small distance. Which is why this many decades were passed. And for each of these small problems, there are many PhDs. For the coating problem now, for the next generation detector, which is called A+, there are several labs with in each one having multiple PhD students. They are trying to explore, and this is essentially a condensed matter physics problem. How to coat the mirror with which material that will reduce this Brownian noise in this in the coating. So the thing is that yes, it is right now they are maintained at the room temperature, but there is this Japanese detector was trying cryogenic very cooled detector, but there are other problems. See, you have to also think about different kinds of other properties, material properties at different temperatures. The temperature. So then what happens is that when all those things are folded in, this so far does not seem to be that easy. People plan to do cryogenic very cool thing because if you cool it, then obviously the Brownian noise will go down, but it is not yet settled. They use sapphire as the material. What LIGO is fused is SiO2, silica. LIGO is silica, but then I think silicon could be a material which could be used for this thing. I don't know exactly this part of it. Okay. Now this is how the detector actually looks like. So these are the vacuum tubes. This is 1.2 meter, and this length is 4 kilometer. Okay, they have of course shown only the parts of it, and these are different chambers. Each of these chambers has basically those components needed for the interferometer. So this is the beam splitter, this is the one mirror, and this is the other mirror which forms the cervical cavity. Okay, and these are other optics. This thing that the laser comes from some point, and all those things happen. Okay. This is now here things may look pretty small, but actually each one of these are this big. Okay. So you see that this is compared to human, this is how big each one of those chambers are, because you can see that a 40 kilo mirror is like pretty big, and then it has to be suspended, and we will come to the suspension part. I thought I will not torture you for 2 days, but it's taking a much longer time than I thought. So here you see this is the suspension, the primary suspension for LIGO mirrors. It's a 4-stage suspension. Now this is also very interesting. That why you suspend the mirrors like this? The thing is that first of all you need a free mass which can move when gravitational waves come. Okay, so the mirrors hanging mass is okay because if they are hanging like this and if gravitational waves are falling, they can move in one direction freely. You don't need the movement from other direction because in this Michelson interferometer for x arm you need x movement and y arm you need y direction movement. That's enough. But then there is this other noise because they are not hanging from the sky. You have to put some mechanism so that they are suspended, but ultimately supported from the ground, right? Because there will be something which is sitting on the ground, which will go to the top, and something will be suspended. But all this ground noise is going to come to the mirror. The ground noise is very large. So how do you take care of that? You see that a very nice way to take care of again this ground noise. It should be such that it should be highly resonant and the quality factor is such very high but the resonance frequency is outside the detection band. That's how it is done here also. Now you see that you can do this very interesting experiment, okay, and you can also imagine it. So suppose you take a stone and hang it with a rope, okay, and then you start moving it like this. You'll see that the stone is moving with this, okay, with your the way you are moving your hand. Now you start moving it extremely fast, okay. You'll see that your hand is moving, but the stone is hardly moving, okay, and that is related to the fact that a forced harmonic oscillator, if you remember those horrible formula which you marked up before the exam, it will be 1 by this omega minus omega square minus omega naught square whole square minus this thing. So this, if you expand, you will see it actually falls as 1 by frequency square when omega is much larger than omega naught. Okay, so basically at higher frequencies, a pendulum acts as a seismic isolation system. It is basically a low-pass filter, high-pass filter. So it allows higher frequencies, but it does not allow the. So it blocks the. It is a what am I saying? It blocks the high-frequency noise. So it's a low-pass filter. It's a low-pass filter. So all the high-frequency noise is actually blocked. So it actually reduces at 1 by frequency square, one stage. But you want much steeper fallout. What do? You add 4 more stages. So you 3 more stages. So you make it 4 stage suspension. So that is, these are these 4 stages. Different stage has many other controls and so on. But this is how the mirrors are suspended. Now from here, then they sit on a seismic stack, seismic isolation stack. So which have many other active and passive isolation. That is, there are springs and rubbers and all those things first, but then there are also sensors on the ground which measure the seismic movement and put a feedback system or feedback control there to reduce the noise, okay, so that it is extremely stable. Okay, so this is sort of the picture of the mirror and all those things. You cannot obviously touch the mirror. If you put a fingerprint, the mirror is gone, because it will create deformities on the surface. With 1 megawatt laser power, those deformities will burst. So there will be small explosions there, and that will destroy, spoil that part of the mirror. So there cannot be the kind of this thing you need. I think it is lambda by 100 or something of that order. It's extremely, has to be extremely smooth. This is the LIGO mirror. This is a pre-stabilized mirror for LIGO, the laser basically. Sorry, not mirror. I'm saying laser for, this is the laser, okay? This is much bigger than the laser pointer we are using here. It's a 70, it is supposed to be, so initially it was supposed to be 125 watt, but I think it generated 70 watts of power. I have to check what is the power right now. So the pre-stabilized ones is basically where you get rid of all unwanted moves. So when you are creating, you're imagining a laser frequency, laser signal as like a Gaussian. Like it is like the center is brightest, and then there are it's like a Gaussian mode. But that is not actually the case. If it is this laser, it is not that way. There are many other modes, okay? And you have to remove those so that you get a perfect interference pattern later on. Because otherwise it becomes very difficult to understand that what is causing disturbances. Okay. And this is the LIGO optics. It looks pretty straightforward, as you can see. So this is just one part of it. So finally, these are the, this was somewhat older. So these are the kind of sensitivity curves that you get. Okay. But one thing to mention here is that I don't think I have that plot. Yeah, I will stop here. But one thing I want to mention here is that I actually had another plot which shows how this sensitivity curve evolved with time. Okay, that is, you have initially something, then after some few years they'll put another curve and so on. So it takes like years to get there. Okay, initially you don't get whatever you expected. The design curve can hardly be obtained. It is always like a dream, sort of you put something on paper, do back of the envelope calculation, and then get something. The real thing is much more tough. And it takes many PhDs, as I'm saying, to reach there. And many times the noise will be unknown. And people have to go there and think and break their head to find out that what exactly is causing that noise. And it could be of fundamental origin, it could be of technical origin, and things like that. Okay, that is what takes a lot of time. Yeah, okay, fine. I think I will, okay. Yeah, okay, let me say one more thing. Yeah, I just wanted to say one thing. See, here you saw some parameters. Here, these parameters are actually part of the whole design process. It is not that these are some separate things. Because people saw availability, whatever they could try out, and then they come up with a design. There is no mathematical rules for doing that. And that's why this research goes on. People come up with different ideas and say that you should not probably come up with a very dramatic idea in some ways, because then you may waste a lot of time in doing that. And I mean, you have to figure out whether people try it. But then dramatic ideas can bring also dramatic changes. So all those there is still a balance, like how much risk you want to take versus how much success you are, meaning how much improvement you are like betting at and all kinds of things. So the thing is that how different each interferometer could be. Like the Virgo interferometer uses a 7-stage suspension system, while LIGO uses 4 stages. So these kind of differences are already there, but there are many other possibilities later on, because people are now thinking about next generation detectors. So these things will come in the last lecture, that what people are doing for the next generation detectors. Okay, I will end here today. Then after this will be now it has again stopped working. Yeah. Okay. All right. Yes. That is the next one. That is the. I mean, people who use different techniques, but now these days people use machine learning. It's quite. I mean, it is becoming more and more popular to use machine learning. But gravitational waves, crudely, gravitational wave signal has a certain feature that it's a chirp signal, that the frequency and amplitude both are increasing with time. So it creates a track in time frequency map. So that track is different from the noise, but noise could also take such a track. But the probability that the track created by a noise in 2 detectors separated by 3,000 kilometers at the same time is extremely low. And that's how you put. So whenever you see a signal, it is always possible that it is a noise. Basically, when we are looking at noise, so people put something called the false alarm probability. But what is the probability that this is a noise rate? And typically the currently accepted false alarm rate is 1 per year. So when you detect, let's say, when you are doing the first detection, you don't want to go for allow a false alarm probability of 1 per year, because then in 5 years you can get 5 false alarm and you are detecting only 1. So that is not acceptable. So initially it was very high, and the first detection at like 65,000, 1 in 65,000 and so on. That is extremely high, but that also because the signal was strong. But right now the accepted value is 1 per year. So you are detecting, let's say, 10 signals per year, and now actually it will become more, probably 100 signals per year. So one signal, one of them is wrong is fine. 99 will be true signal.
How can we define the lasers so that it is coherent over 4 kilometers?
So the thing is that this laser is actually so there is this is coupled to the cerebral cavity. Okay, so actually the laser frequency is also tuned in the same process. Okay, so usually I have to check that how much is the coherent length of the laser. But typically, I think this is within acceptable values, meaning that when you have a stabilized laser with very narrow frequency band, I think it can stay coherent for thousands of kilometers. But I checked that. I did not check. I mean, in a fabrical cavity, it actually does not operate in exactly in that way because you are holding the laser, holding this thing at a resonance. So I told you right that the interferometer picture is not exact. I mean, this is roughly good. It is not how actually LIGO operates. The thing is that about favorable cavity, yeah, this is an important thing. I forgot. It's very interesting. That when you have this favorable cavity is resonant only in a very narrow frequency band. If you change the frequencies or the distance even slightly, the whole resonance falls off. Okay, so it has so you can put either so it has something like this. Okay? So this kind of thing. It could be frequency, it could be distance, and so on. The thing is that when gravitational waves falls on the detector, then the mirrors will get displaced, then immediately you will lose power. So that is not how, that is why that model, that simple picture cannot be used for gravitational detector. What is done is a feedback control. The detector is always in a locked state. A locked state means that it is always maintaining the resonant condition. It is locked at resonance. As soon as the detector tries to move out, okay, so suppose it is at the dark fringe. Okay, so suppose that is you are at the middle of the dark part of the thing. So why you want to be at the dark fringe? Because if you then the fractional change when gravitational waves fall would be larger. If you are at a bright fringe, then the fractional change will be very small. So you want to be at the dark fringe, okay, where the gradient is high. So basically what I mean is that, so let's say this is a fringe pattern. If you are here, then the fluctuations will be high. But this is also not completely correct because you could be here also. The problem at this dark fringe is that if you move this way or that way, you will see exactly the same variation in power. So the system, the feedback control system will not understand whether you are moving this way or that way. So rather, you could put your this thing here. Okay. Then what happens is that by looking at the gradient, even though it is still image pretty dark, but by looking at the gradient, you would know that which way the detector is trying to move, and you put a feedback control actuation signal to hold the mirror at the right place. This feedback signal is the gravitational wave signal, meaning is taken as the main signal, which can be due to noise, which will have astrophysical component also, but this feedback signal is the final signal. The mirrors actually don't move. Okay? Yes.
How do you choose suitable laser for that?
Oh, this is like it is like there is a whole big group who works on that in Germany, in Hanover. So they build this laser. So the laser power is already we decide from calculation that we need this much laser power. Actually, all these things go hand in hand. You know, it is like this Galileo's thing that you see what is the cutting edge technology available. If you say I need a 10,000 watt continuous laser, the people will say it is not available right now. So they see what is the maximum laser power available, and based on that they tune rest of the design. Because ultimately you have to reduce cost. That is the fundamental thing. I mean, all these things we say science, this, that, etc. Ultimately, you have to reduce the money. And reducing money means you have to use the available technology in every different field at the same time. Otherwise, you could say you may be demanding too high technology, which is not there in one part. On the other hand, in another part, you will be demanding something which is really trivial. So then you are breaking the balance. The best thing is to go like uniformly in every part of it, you will use the cutting edge technology. So then the cost will be minimized, and also you will be able to deliver in a reasonable time frame. Otherwise, you have to wait for there will be a bottleneck. That is, you have to wait for one technology to develop for a long time.
Does the wavelength of the laser change as the
No, the wavelength of the laser does not change.
But the metric has
The metric changes. There is a nice paper written by Peter Solson on that, addressing precisely that issue. that laser, even if it did change, meaning if you go to a frame where it is, you will see that the laser frequency is changing. Ultimately, you will get the phase change, right? The phase change that is happening is kind of, it's a fixed quantity. Okay. So people did consider that what happens if like laser is also changing with the gravitational, but that is not a good concept. I mean, in my interpretation, it was that this H00, that TT gauge does not change, so the frequency of the laser would not change. But then there are the other interpretations. So you can see this is by Peter Solson. Okay. He has a small note on that.
Is it intuition?
It is not exact. I mean, it is that thing. I think it is an American Journal of Physics. It is not really very complicated, but it is done with diagrams, basically. That how the phase changes and things like that. All those things have been done. Okay.
So I think you can say this Laplace chair.
That is right. There is a different count there. Okay. Oh, there was a question earlier which did not come to my list. How H plus and H cross are independent? It looks like they are related by a rotation. No, they are. So, for example, okay, you can take the electromagnetic wave example, right? There are two polarizations which are at 90 degrees. A 90-degree rotation would basically make X the Y. So they are clearly independent, but it is like that the distortion which is produced in one direction by the plus polarization to that, let's say, beam of particles, if you could be produced, the same one could be produced by the cross polarization if you rotate it by 45 degrees. That's what it means. I mean, it is the same thing, which is like either you apply the rotation to the incoming wave or to the system of particles and things like that.
So what polarization is like emitted by the logic?
Both. Usually both polarizations are emitted. Because it is not like you are exactly in a fixed pair. In fact, it's circular polarization. I mean, when you see that this binary, you see phase on, it will be going like this. So it is not a fixed polarization. Both will be there.
So you'll see some combination.
It will say linear combination of the polarizations. So, but your detector, the detector frame will only detect cross polarization. The detector cannot detect the cross polarization in the detector spec because it only is sensitive to the cross polarization. If you imagine that figure, will generate distortion at 45 degrees. So this arm and this arm will expand and contract exactly in the same way, which basically means that in the detector's frame you will get the cross polarization. But in the source frame, the source is oriented in a certain way, then there is a wave frame and so on. So it is very different. But you will get the projection. Basically, you will get the component. So what is coming to you? It is like a polarizer. I mean, suppose you have a polarized light which is in some direction, or a circular polarization, whatever. You have another polarizer which is in certain way. Then you will see the component of this polarization in your polarizer. So that's how it is. Okay? All right. End of this lecture.